Hi everybody. Here I have taken a 10-story building. It is office building. It has 6 bay of 7.5 meter in the east-west direction and 3 bays of 6.5 meter in the north-south direction. I can see here I put the direction north. And all the columns are 400 millimeter by 400 millimeter. And my target is to design these two shear wall because wind load acting on the long side of the building, this long side of the building, wind load is acting in this direction. Already I put here directions, so wind load is acting in this direction. So surely that load is resisted by these two shear walls. And these two shear walls are equal and symmetric. So I have to design only one. And this is my third video for shear wall design. In the first video, I computed wind loads. In second video, I computed dead load and live load. So wind load, dead load and live load, all those loads, I have to bring it in this video and to use it to design the wall for shear and flexure. So let's move ahead to see how to do that. And please subscribe my channel, EduStube. So as I said, this is the shear wall and wind loads are acting on each floor. And I showed how I got all these values in my first video. I showed it, and from this wind load I got this shear force diagram and moment diagram. But I have to take these two values. One is 1787 from here and 35,376 kilonewton meter. Both are on first floor, and I will use this to design the shear wall in terms of shear and flexure. So let's move taking these two values. Also, here you can see a table, dead load and live load on one wall. Actually, this table I made in my second video, and I showed there how I got this value, I mean dead load, snow load, unreduced live load, tributary area, live load reduction factor, and reduced live load, then total live loads. So in second video, I just showed in details how to reach up to this table. But from this table now, in this video, I need these two values. So 7758 and 1817. This is for dead load and this is for total live load. So let's take this value and move ahead. So what I'm doing, this is the shear wall. So as I said, I brought some value from previous two slides. One was 35,376. That was for two walls, so it will be divided by 2. So 17,688 kilonewton meter per wall. This is moment. And in the first floor here, I have shown here, this is this MF. Then for shear, it was 1787. Surely it will be divided by 2 to get this load per wall. And I showed it here, BF, acting like this. Then axial load. In the table, I showed dead load and live loads. So these two forces I brought. So these are the forces acting as a PF in this direction. And the shear wall number 1, T equal to 250 millimeter and length equal to 6900. How it comes, I showed it in my second video on shear wall design. So let's move, taking all this one, this one, this one, I mean this one, because one important thing here I want to mention, that this loads, it is without any factor. I mean it is not factored loads. It is not factored because I did not use any factor. And another important thing is each floor height is 3.5 meters. Only first floor is 4 meters. Parapet is 500 millimeter. So let's move ahead. Here I can see the load combination, which is very important because after getting load combination, we can think of start designing. So load combination 1 and combination 4. I am interested for these two. Why load combination 1? Because it gives the largest axial load is from combination 1. If you look at, you will understand this dead load, live load. We know these two loads. Already we have seen in previous slides. So this and this, how it comes, it will be this, because we have to take like this, 1.25 multiplied by dead load, 1.5 multiplied by live load, we get this. Axial load, this is factored loads, combination 1. But for combination 4, it is very interesting because here 0.85 dead load. Why 0.85 dead loads? Critical load combination for moment is combination 4. Why it says like that? Because this load combination 4, it will require most reinforcement because it has smallest axial load. Look at 0.85D. So it is 6595. So this combination 4, it takes smallest axial load, and this combination will require most reinforcement. There is a moment here 35376 multiplied by 1.5 at an end divided by 2, we get 26,532 kilonewton meter per wall. It is factored 1.5. Shear force also factored, we get 1341. Now I put red mark for this one, this one, this one and this one, because we are going to use this to design the wall for shear and for flexure. So let's move. So here in Excel, I am going to show you how to calculate minimum reinforcement, and after that we will compute the axial load resistance of the chosen wall. As well, I'll show you how to design for shear and also for flexure. So let's start with minimum reinforcement. According to CSA standard A23.3, to find vertical bar, we shall use this 0.0015 AG. To find horizontal bar, I mean minimum reinforcement horizontal bar, 0.002 AG. So for vertical bar, if we use this, say S, it will be equal to 2588 millimeter square, and it is for the whole wall. Next, we need to find maximum spacing. But there is a way to find. We have to get 3T or 500. Which one is smaller? So let's check that. 3T means 750 or 500. Out of these two, 500 is less. So we must choose 500 millimeter spacing. Again, if we go for choosing the number of steel, say 14 numbers, 10 bars. So what will be the area of the steel? 2800 millimeter square for 2 layers. Again, 2 extra bar at 50 millimeter from each end of the wall we have to choose. So totally we are getting 14 plus 2, 16 number 10 bars. and area will be 3200 millimeter square. So vertical bar we got area of the steel 3200 and spacing 500 millimeter. Now let's check for horizontal bar. Two layers of number 10 bars. Surely we can write spacing equal to this 2AB divided by 0.002T. So putting the parameters values 250, 100, we get 400 millimeter. Easily we can write use number 10 bars 400 millimeter spacing. This is for horizontal bars. Number 10 bars. Be sure with. So we got vertical bar, we got horizontal bars. Now let's go for axial load resistance of the chosen wall. According to empirical methods, axial load resistance, factored axial load resistance can be determined based on this equation. And also we must assume that axial load factor in the middle third of the wall. That should be assumed. Now question is about the parameters which is on these equations. Alpha 1, phi c, a prime c, ag, all we know. Here one new things we got k. K actually it is assumed as 0.8 since the wall is restrained against translation and against rotation at both ends. Otherwise value would be different, but in this situation it will be 0.8. H we know it is thickness, wall thickness, it is 250. But LC, how to get this? Clear height. Clear height means our floor height is 3500. Floor to floor height is 3500. But we have to subtract from 3500 250. That 250 comes from 200 from the slab and 50 from the drop panel. So total 250. So we get 3250 millimeter clear height. So once we put all these value for these parameter as well as this, we get this value and it is in Newton. So in kilonewton it will be 14,903 kilonewton. This is factored axial load resistance. It means it is able to carry this load. But actually we are imposing on this wall factored axial load 12,424 kilonewton. It is applied on this wall. So surely we are in safe condition because it can carry more than this. So it is okay. Now let's move for design for shear. So design for shear, factored shear in the bottom story. It is VF equal to 1341 kilonewton per wall. Already we know that. This is from the shear diagram at the bottom story. We got this value. It is per wall. But CSA standard, it says VF less than equal to VC plus VS. This VC means shear force resisted by concrete and VS means shear force resisted by shear reinforcement. Now this VC, concrete shear resistance, it is equal to this equation, because the minimum vertical reinforcement is distributed over the horizontal length of the wall. We know there was minimum vertical reinforcement will be on this wall at least. So our VC equation will be like this. Important point is for that reasons it is here 0.2. We need to find dV also. It will be 0.8 length of the wall. So it is 5.52. So all the parameters, if we put the value for this parameter, our value comes as this in Newton. One thing I want to mention, I forgot this. Say if I click here, this one, you see the whole formula, whole equation, I put it here. Taking the all values cell address, I put here according to this equation, and we got this value. Same way for this one also, for shear, I use this equation, putting all the values of parameters as a cell address. So I got this value. In kilonewton, it will be 907. So one important things we have to check. What is that? VF already I saw, or I told, factored shear in the bottom story, I told it is 1341 kilonewton per wall. But our wall, concrete shear resistance of our wall, it is 907 kilonewton. So what about the balance? Of course, this balance 434, it must be resisted by shear reinforcement. So that shear reinforcement we have to calculate using this. Vs, shear force resisted by shear reinforcement, it will be equal to this, and rearranging we can write it as AV by S equal to Vs by this, and then putting the value of all these parameter as well the Vs we can take from here, we get 0.23 millimeter square per millimeter. That is the requirements. If we provide more, it is good. So what we will do, we will try number 10 horizontal bar at 400 millimeter on each face. So this same ratio AV by S, AV means here 200 because it is on each face, so it will be on two face. So 200 divided by S is 400, so 0.5 millimeter square per millimeter. So what we found here, if we compare this and this, so surely we are in safe situation. This is more than enough in bottom story. So use 10 number 10 bars, I mean horizontal bar at 400 millimeter on each face. So we got it. So we did design for shear. Now design the wall for flexure. Design the wall for flexure. So what we will do? Axial load on the wall, it is less than the balance load. As well the load combination 4 load combinations 4 means 0.85 dead load plus 1.5 wind loads. Already we have seen this in previous slides. That was the load combination 4. And that combination will require most reinforcement because it has the smallest axial load, because we are taking 0.85 dead load. And in the first story, already we have seen this was the value for axial load 6595, and this moment was 26,532, and this moment was due to the wind load. Now, first we shall compute the moment resistance of the wall with two curtains of say 16 number 10 vertical bar. Of course, we remember this term. We found this in case of minimum reinforcement, and it was 3200 millimeter square. Now, we will compute this moment resistance of the wall using this reinforcement. That is very important point here to understand design of wall for flexure. The ratio of the distance from extreme compression fiber to the neutral axis, it is called C. Also we know length of the wall is LW. So surely we can take the ratio of this C and LW equal to, this is the equations, but the question is these parameters we need to know: omega, alpha, alpha 1, beta 1. Alpha 1, beta 1 already it is here, 0.805, 0.895. What about omega and alpha? Omega and alpha, these two, we can use these two equations. So omega, if you look at this right hand side, you will see all these parameters are related with steel, phi s, fy s. And here it is related with concrete, phi c, f prime c, lwt. This is the cross sections of the shear wall. So once we get this ratio, it is omega. What about alpha? Alpha means PF, this axial load, divided by all these parameters. This is totally related with concrete and the cross-sectional area of the shear wall. Here it is axial load. So ratio, it will give us alpha. So 0.212. Now, it's very easy for us to find C by LW because we already got all the parameters. So at an end we got 0.313. Neutral axis, it will be C equal to this multiplied by LW, it will be 2160. So we got the neutral axis depth. Now, to find the moment capacity, actually it is an approximate equation, and this equation, it is proposed by Cardenas and Magura. They propose this equation. And another important things we have to look at this equation. As I said here, we shall compute moment resistance of the wall with two curtains of 16 number 10 vertical bars. Area is 3200. This is actually this 3200. We have to use it here. Look at, already it is here, 3200. Also, we have to bring this PF also here, this PF. And C by LW. This ratio also we have to use. It is here. So putting all these parameters, value for all these parameters, we get this. If you look at this position, I put this whole equation, values, selecting all the cell address. So Excel calculated that results. And at an end, I wrote 18,210 kilonewton meters. But look at here, our wind loads, we calculated this moment due to wind loads 26,532 kilonewton meters. But moment resistance, as per these approximate equations, we got 18,210 kilonewton meters. So of course this is less from this. So, and one thing you have to keep it in your mind, to calculate this, already we use the minimum reinforcement, already it is added here, 3200. Till then it is not satisfying. So the balance what we have now, we have to use this to find the additional reinforcement. So we shall place extra reinforcement in the boundary elements located at 200 mm from each end of the wall. Extra reinforcement in boundary elements located at 200 mm from each end of the wall. If you imagine what is the wall, then you think of both ends. It will be 200 from both ends. So surely our length was 6900. So minus 400. So central part is come 6500 millimeter apart. So for this part, additional vertical steel area we have to calculate. So what we will do, additional vertical steel area we shall calculate, already we know this one minus of this to get the difference, divided by 0.85. We know what it is, 0.85 means phi s, this is Fy, and this is 6500, already we got it here. We get 3766 millimeter square at each end of wall. At each end of wall. So what we will do, this reinforcement will provide as 6 numbers 30 vertical bar at each end of the wall. It will be on both ends of the wall. 6 number 30 vertical bar. What we will do, 2 at 6, 5, 2 at 1 to 5 further in from each end of the wall, or 2 at, I think this is not that much important to give. It can be arranged, but it will be within that 200s. So, or we can provide that, it's not a problem. 2 at 65 millimeter from each end of the wall, 2 at 125 millimeter from further in from each end of the wall, 2 at 125 millimeter further in from each end of the wall. I think we are done for design the wall for flexure. I think that's all for the shear wall designing. So this is cross section of shear wall. We can see here 6 number 30 bars and all this is steel. It is this one, vertical number 10 at 500 millimeter each face. I mean these all bars, these all, I mean this is vertical bars. As it is section, this is vertical bars. Number 10, 500 millimeter each face, I mean on both sides. And horizontal bar, it is this one, already I marked here, this and this. Number 10 at 400 millimeter each face, on both face. And here already I told 6 number 30 bars. I think that's all for this shear wall design. And thanks for watching. Please subscribe my channel.